Silicon-based life and carbon chauvinism, the cosmos and the definition of life. The universe is an expanse of such staggering magnitude that the human mind struggles to comprehend its true scale. With hundreds of billions of galaxies, each containing hundreds of billions of stars, the statistical probability of Earth being the sole cradle of life seems vanishingly small. As humanity gazes upward, utilizing increasingly sophisticated telescopes and spectroscopic analysis, the question shifts from whether life exists elsewhere to what that life might look like. For decades, science fiction has populated our collective imagination with humanoids, reptilians, and insectoid creatures that, despite their superficial differences, operate on the same fundamental biological principles as life on Earth. They breathe oxygen, they consume water, and they are built from carbon. This tendency to project our own biochemical architecture onto the rest of the universe is a phenomenon known as carbon chauvinism. It is a bias rooted in the fact that we have only one data point for life, the biosphere of Earth. However, astrobiology, the scientific field dedicated to the study of life in the universe, challenges this assumption. It asks whether the laws of physics and chemistry permit life to arise from different building blocks. Among the periodic table of elements, one candidate stands out above all others as a potential rival to carbon. That element is silicon. To understand the plausibility of silicon-based life, we must embark on a deep journey into atomic structure, chemical bonding, planetary geology, and the philosophical definitions of life itself. The concept of carbon chauvinism. The term carbon chauvinism was popularized by the astronomer Carl Sagan in the 1970s. It describes the assumption that extraterrestrial life will be constructed from carbon and require water as a solvent, simply because that is how life works on Earth. This view is not necessarily born of arrogance, but of pragmatic observation. On Earth, carbon is the backbone of every known organism, from the microscopic bacteria living in hydrothermal vents to the blue whales navigating the oceans. Carbon forms the complex polymers, proteins, carbohydrates, lipids, and nucleic acids that make the machinery of life possible. Because we have never observed life based on any other element, it is natural to look for what we know. When astronomers search for biosignatures on exoplanets, they look for methane, oxygen, and water vapor, the chemical fingerprints of a carbon-based biosphere. However, critics of this approach argue that it limits our search. If we restrict our definition of life to carbon-based organisms in water-rich environments, we might stare directly at a thriving alien ecosystem and fail to recognize it because it does not fit our preconceived mold. Carbon chauvinism may blind us to the weird, the exotic, and the truly alien possibilities that chemistry allows. To determine if this chauvinism is justified, we must first understand why carbon is so successful. The chemical mastery of carbon. Life, at its most fundamental level, is chemistry. It is the organized manipulation of energy and matter to sustain a state of low entropy. To achieve this, life requires complexity. It needs molecules that can store information, like DNA, molecules that can catalyze reactions, like enzymes, and molecules that can form structures, like cell membranes. Carbon is uniquely suited for this task due to its position on the periodic table. Carbon has 4 valence electrons, meaning it can form 4 stable covalent bonds with other atoms. This property, known as tetravalence, allows carbon to act as a connector, a central hub around which complex molecular geometries can be built. Carbon atoms can bond with other carbon atoms to form long chains, branching trees, and closed rings. This ability to catenate or link to itself is the secret to the diversity of organic chemistry. There are millions of known carbon compounds, more than all other elements combined. Furthermore, the bonds carbon forms are strong enough to be stable in the environment of Earth, yet not so strong that they cannot be broken to release energy. This balance is crucial. If bonds are too weak, large molecules fall apart. If they are too strong, the organism cannot metabolize nutrients or grow. Carbon occupies a Goldilocks zone of chemical reactivity. Additionally, carbon forms stable double and triple bonds, adding another layer of structural variety and electronic properties to biological molecules. When combined with hydrogen, oxygen, nitrogen, phosphorus, and sulfur, carbon creates the rich palette of chemistry we call biology, the silicon contender. If we are to replace carbon, we must look for an element that shares its key properties. The periodic table is arranged in groups of elements with similar electron configurations. Directly below carbon in group 14 sits silicon. Like carbon, silicon is tetravalent. It has 4 valence electrons and can form 4 bonds with other atoms. It is the second most abundant element in the Earth's crust, vastly outnumbering carbon in terms of raw quantity. If abundance were the only factor, life on Earth should have been silicon-based. The fact that silicon shares the same group as carbon suggests that it should have a similar chemistry. Indeed, in science fiction, silicon is the go-to element for non-carbon life. The Horta from Star Trek and the xenomorphs from the Alien franchise are often speculated to have silicon-based biology. In theory, one could imagine a silicon biology where silanes, silicon-hydrogen compounds, replace alkanes, carbon-hydrogen compounds, and silicone polymers replace protein chains. The analogy seems perfect on the surface. Just as carbon forms methane, CH4, silicon forms silane, CH4. Just as carbon forms long chains, silicon can form polymers. However, when we zoom in to the atomic level, the differences between these two elements become stark and problematic for the potential of life. The atomic differences. The primary difference between carbon and silicon is the size of the atom. Silicon has an extra shell of electrons compared to carbon, making the atom significantly larger. This increased radius has profound effects on how silicon bonds with other atoms. The bond between 2 carbon atoms, Cc, is strong and stable. The bond between 2 silicon atoms, Cc, is much weaker. While carbon atoms can link together in chains of thousands or millions to form the backbone of DNA or proteins, silicon chains become unstable as they grow longer. Long silane chains tend to spontaneously decompose, especially in the presence of water or oxygen. This makes it difficult for silicon to form the massive, complex macromolecules required for genetic information and structural complexity. Furthermore, because the silicon atom is larger, it struggles to form double or triple bonds. Carbon frequently forms double bonds with itself, C equals C, oxygen, C equals O, and nitrogen, C equals N. These double bonds are essential for chemical reactivity and the structure of many biological molecules. Silicon, by contrast, rarely forms stable double bonds. The orbital overlap required for a double bond is difficult to achieve with the larger, more diffuse electron clouds of silicon. This limitation severely restricts the chemical vocabulary available to a silicon-based organism. The oxygen problem. Perhaps the greatest hurdle for silicon-based life is its interaction with oxygen. On Earth, carbon-based life engages in a respiratory cycle where carbon compounds are oxidized to release energy. The waste product of this reaction is carbon dioxide, CO2. CO2 is a gas at terrestrial temperatures and pressures. It dissolves easily in water and can be readily exhaled or diffused out of a cell. This makes waste disposal incredibly efficient for carbon life. Now consider the silicon equivalent. If a silicon-based organism were to breathe oxygen and oxidize silicon to release energy, the waste product would be silicon dioxide, SiO2. Silicon dioxide is not a gas. It is a solid, In its crystalline form, it is quartz or sand. This presents a massive engineering challenge for a biological system. How does an organism exhale a solid crystal? If a silicon creature oxidized its food, it would essentially fill itself up with sand and turn to stone. To avoid this, silicon life would likely have to exist in an environment with no oxygen, or it would have to utilize a metabolic process that does not result in the formation of solid silica. This suggests that if silicon life exists, it likely does not resemble the aerobic life forms of Earth. The solvent question. Life requires a medium in which chemical reactions can occur. On Earth, that medium is liquid water. Water is an incredibly versatile solvent. It is polar, meaning it can dissolve a wide range of substances, and it has a high heat capacity, which helps regulate temperature. However, water is deadly to silicon chemistry. Many silicon compounds, such as silanes and silicon halides, react violently with water. If you placed a complex silicon-based molecule in a bucket of water, it would likely hydrolyze and fall apart. Therefore, silicon-based life would require a different solvent. Several candidates have been proposed by astrobiologists. Liquid methane and ethane are hydrocarbons that exist as liquids at extremely low temperatures. On Saturn's moon Titan, there are lakes and seas of liquid methane. In such a non-polar solvent, silicon compounds might be more stable. Another possibility is liquid ammonia, or even sulfuric acid. Each of these solvents has its own range of temperatures and pressures where it remains liquid, and each would dictate a completely different biochemistry. For silicon life to thrive, it would likely need a solvent that does not attack its molecular backbone, suggesting that cold, anhydrous worlds are better candidates than warm, watery ones. Titan as a laboratory. Saturn's moon Titan is often cited as the most compelling location in our solar system to look for exotic life. Titan is the only moon with a dense atmosphere, and it is the only world other than Earth known to have stable bodies of liquid on its surface. However, these are not bodies of water. They are bodies of methane and ethane. The surface temperature of Titan is approximately -179 degrees Celsius. At these temperatures, water is frozen as hard as granite and acts more like a rock than a solvent. However, the hydrocarbon lakes offer a medium for chemistry to occur. Some scientists have speculated about the possibility of, quote, azotosomes, hypothetical cell membranes made of nitrogen compounds that could function in liquid methane. While this is distinct from silicon life, Titan represents the kind of environment where silicon chemistry might overcome its instability issues. In the deep freeze of Titan, the weak seaside bonds might be stable enough to endure. Reactions that are too fast and explosive on Earth would be slowed down to a manageable pace. While carbon is still more abundant on Titan, the absence of liquid water and oxygen removes the two biggest threats to silicon chemistry. If we are to find non-carbon life in our backyard, Titan is the place to look. Silicone biochemistry. While pure silicon chains, polysilanes, are unstable, there is a class of silicon compounds that are remarkably durable: silicones. Silicones are hybrid molecules featuring a backbone of alternating silicon and oxygen atoms, SeO-SeO, with organic side chains attached to the silicon atoms. The SiO bond is extremely strong and heat resistant. This is why silicones are used in everything from kitchen spatulas to medical implants and high-temperature lubricants. Some astrobiologists have hypothesized that silicon-based life might actually be silicone-based life. In this scenario, the organism would utilize the alternating silicon-oxygen backbone to build its polymers. This would solve the stability problem, as these chains can survive high temperatures and harsh environments. However, the strength of the SiO bond is a double-edged sword. While it provides stability, It makes the molecules very difficult to break down and rearrange. Life relies on the constant making and breaking of bonds to store and release energy. If the bonds are too stable, metabolism becomes impossible. The organism would be inert. For silicone life to exist, it would need enzymes capable of cracking these tough bonds with high efficiency, likely requiring high-temperature environments or exotic catalysts not found in terrestrial biology. Planetary conditions for silicon life. Given the constraints of silicon chemistry, what would a silicon planet look like? It would likely not be an Earth-like blue marble. If the organism relies on low-temperature solvents like methane, the planet would be far from its star, a frozen world of hydrocarbon mists and cryogenic oceans. In this cold silicon scenario, metabolic rates would be incredibly slow. A silicon creature on a Titan-like world might take years to take a single step or process a single thought, living on a timescale vastly different from our own. Conversely, there is the hot silicon hypothesis. Because the SiO bond is so heat-resistant, perhaps silicon life exists on worlds that are too hot for carbon life. On a planet with surface temperatures of hundreds of degrees, carbon molecules would denature and burn. Silicones, however, might remain stable. This leads to the speculation of silicon life existing on high-pressure, high-temperature worlds, perhaps even deep within the crust of a planet, rather than on the surface. However, the solvent problem remains. Liquid water cannot exist at such high temperatures unless under extreme pressure, so the medium of life would have to be something exotic, perhaps molten salts, or even liquid rock. The biosignature challenge. One of the most practical problems in the search for silicon life is that we don't know what to look for. When astronomers analyze the light passing through the atmosphere of an exoplanet, they look for biosignatures, gases that are produced by life and accumulate in the atmosphere. For carbon life, we look for the simultaneous presence of oxygen and methane, a combination that is chemically unstable and requires constant replenishment by a biosphere. For silicon life, the biosignatures would be totally different. If silicon life exhales solids, it wouldn't leave a gaseous footprint in the same way. We might look for unusual ratios of silicon isotopes, or the presence of exotic silane gases that shouldn't exist naturally. However, distinguishing these signals from geological activity would be extremely difficult. Volcanoes and geothermal vents release a vast array of chemicals. Without a clear understanding of silicon metabolism, differentiating a breathing planet from a geologically active one is a monumental task. This is the n=1 problem again. Until we find a second example of life, we are guessing at the fingerprints it might leave behind. The shadow biosphere. A fascinating hypothesis in astrobiology is the concept of a shadow biosphere, right here on Earth. The idea is that if life originated more than once on our planet, there might be microbial life forms coexisting with us that have a completely different biochemistry. Because our tools are designed to detect DNA and proteins, we would be completely blind to these shadow organisms. Could there be silicon-based microbes living in the Earth's crust or in high-temperature vents, unnoticed by science? While intriguing, this is considered unlikely for silicon specifically. Silicon is incredibly abundant in Earth's crust. Rocks are mostly silicates. Yet we see no evidence of it being incorporated into complex metabolic machinery. Biological systems are usually opportunistic. If silicon were useful and available, carbon life would likely have evolved to use it. Diatoms and some sponges do use silicon to build structural shells, but this is closer to a human building a brick house than a human being made of bricks. The silicon is used as armor, not as the fundamental stuff of life. The lack of silicon integration in terrestrial biology, despite the element's ubiquity, is a strong argument that carbon is simply the superior biological building block in Earth-like conditions. artificial silicon life. There is, of course, a form of silicon life that is rapidly evolving on Earth right now: artificial intelligence and computer hardware. While not biological in the traditional sense, computers are based on silicon chips. They process information, consume energy, and, with the advent of AI, are beginning to display learning and autonomous decision-making. Some philosophers and futurists argue that the destiny of life in the universe is to transition from carbon-based biology to silicon-based technology. In this view, biological life is merely a bootloader for machine intelligence. Silicon allows for information processing at speeds millions of times faster than biological neurons. It is durable, capable of surviving in the vacuum of space, and can be repaired and upgraded. If we encounter extraterrestrial intelligence, it is statistically more likely to be a silicon-based machine civilization than a biological crew. These entities would not be alive in the squishy chemical sense, but they would fulfill many of the criteria for life. They would consume energy, resist entropy, and potentially reproduce by building more machines. This blurs the line between the biological definition of silicon life and the technological definition. The role of chirality. Another subtle aspect of biochemistry is chirality, or handedness. Biological molecules like amino acids and sugars exist in two mirror image forms, left-handed and right-handed. Life on Earth uses almost exclusively left-handed amino acids and right-handed sugars. This homochirality is essential for the specific lock-and-key mechanisms of enzymes. Achieving this handedness in silicon chemistry is more difficult. While silicon can form chiral centers, the larger size of the atom and the flexibility of its bonds make it harder to maintain the rigid 3D shapes necessary for highly specific enzymatic reactions. Carbon's ability to hold a rigid shape is one of its unsung superpowers. Without this rigidity, the complex machinery of proteins would be floppy and ineffective. For silicon life to exist, it would need to overcome this floppiness, perhaps by operating at very low temperatures where thermal energy is low and molecules become stiffer. This reinforces the idea of silicon life being a phenomenon of the cold universe, boron and other alternatives. While silicon is the primary contender against carbon, it is worth briefly mentioning other possibilities to contextualize the uniqueness of group 14. Boron, for example, has a fascinating chemistry. It can form complex clusters and cages, boranes. However, boron is relatively rare in the universe compared to carbon and silicon. Nitrogen and phosphorus can form long chains and rings, but they tend to be unstable or highly reactive. Sulfur can form chains, but they are simple and lack the complexity needed for information storage. Metal oxide life has been theorized for conditions inside stars or in high-energy plasma environments, relying on magnetic forces rather than chemical bonds. But among all these speculations, silicon remains the most grounded in conventional chemistry. It is the closest cousin to carbon, sharing the tetravalency that makes complexity possible. The failure of other elements to offer a viable alternative only highlights how special the carbon-silicon relationship is. They are the two titans of complexity in the periodic table, the rare Earth hypothesis versus galactic abundance. The debate between carbon chauvinism and silicon hopefulness ties into the broader debate about the abundance of life. The rare Earth hypothesis suggests that the specific conditions on Earth, liquid water, a magnetic field, a large moon, plate tectonics, are incredibly rare, and that complex life is therefore unique to our planet. If life requires carbon and water, then the habitable zones of the universe are narrow. However, if silicon life is possible, the habitable real estate of the cosmos expands dramatically. It would mean that life could thrive on hot Venusian worlds or cold Titan-like moons. It would mean that the Goldilocks zone is not a thin strip around a star, but a broad spectrum of environments. Breaking free from carbon chauvinism is an act of optimism. It assumes that the universe is creative and that life is a fundamental imperative of matter, not a lucky accident of chemistry restricted to one specific set of parameters. The thermodynamic argument. Thermodynamics governs all physical processes. For life to exist, it must extract energy from its environment to create order. Carbon chemistry is favored thermodynamically on Earth because the energy required to form and break carbon bonds is comparable to the thermal energy available in the environment and the energy provided by visible light. Silicon bonds, particularly SiO, are very deep energy wells. Once formed, it takes a lot of energy to get them out of that state. This suggests that silicon life would have a much harder time scavenging energy. It might require high-energy sources, such as direct UV radiation or extreme thermal gradients, to drive its metabolism. This adds another constraint. Silicon life might need to live near energetic stars or powerful geothermal sources, but those same sources emit radiation that could destroy complex molecules. Carbon life exists in a delicate balance of energy flow. Silicon life would face a steeper thermodynamic hill to climb. Science fiction representations. It is impossible to discuss silicon life without acknowledging the role of science fiction in keeping the idea alive. Writers have long used silicon as a shorthand for truly alien. The Tholians from Star Trek, crystalline entities that live in high temperatures, represent the hot silicon hypothesis. The idea of living rocks or crystal beings appeals to the human imagination because it bridges the gap between the animate and the inanimate. However, sci-fi often ignores the chemical realities. It rarely deals with the waste disposal problem or the solvent issue. It treats silicon as carbon with a different skin. Real scientific analysis shows that silicon life would be fundamentally different in speed, structure, and interaction with its environment. It would not just look different, it would be different in every measurable way. It might move so slowly that we perceive it as a statue. It might communicate via electrical impulses through the ground rather than sound waves. The true alienness of silicon life is likely stranger than fiction. Future missions and experiments. How do we move this debate from theory to fact? We need to explore. Missions to Titan, such as the proposed Dragonfly rotorcraft, are crucial. By landing on Titan and analyzing the chemistry of the hydrocarbon lakes, we can see if complex prebiotic chemistry is occurring. We can look for patterns in the distribution of chemical elements that defy random chance. Laboratory experiments on Earth are also vital. Synthetic biologists are attempting to force silicon into carbon-based organisms, evolving enzymes that can create carbon-silicon bonds, organosilicons. While this isn't creating silicon life, it is testing the limits of how silicon can be integrated into biology. Directed evolution experiments could eventually produce a semi-synthetic organism that uses silicon for some structural or metabolic functions, proving that the two chemistries can coexist. The philosophical implications. If we were to discover silicon-based life, the philosophical implications would be shattering. It would prove that the tree of life has more than one root. It would mean that biology is not a singular miracle, but a universal law. It would force us to redefine life, not by its components, DNA, RNA, protein, but by its processes, metabolism, reproduction, evolution. It would humble us, removing the last vestige of specialness we attach to our carbon-based nature. We would be just one flavor of life in a universe of infinite variety. Conversely, if we search the galaxy and find only carbon life, it would be equally profound. It would suggest that there is a universal bottleneck, a great filter of chemistry that channels all life into the same carbon-based path. It would mean that we are chemically kin to every being in the cosmos, united by the specific properties of the carbon atom. Valence and geometry in detail. To truly appreciate the struggle of silicon, one must visualize the geometry. Carbon atoms in a diamond lattice form a perfect tetrahedron. This structure is incredibly hard. Silicon also forms this lattice, as in pure silicon crystals used in chips. However, life requires flexibility. Carbon can switch between sp3, tetrahedral, sp2, flat planar, and sp linear hybridization. This ability to change shape allows proteins to fold and enzymes to function. Silicon is reluctant to hybridize in the sp2 or sp configurations. It wants to stay in the tetrahedral shape. This makes silicon chemistry rigid. Imagine trying to build a machine where none of the parts can bend or pivot. That is the challenge of building a cell out of silicon. You can build a structure, but can you build a machine? This rigidity is why rocks, mostly silicon, hold their shape for billions of years, while bodies, mostly carbon, change and decay. Life is a dance of instability, and silicon hates to dance. The interstellar medium. Interestingly, we detect silicon in deep space. In the interstellar medium, the vast clouds of gas and dust between stars, we find complex molecules. Most are carbon-based, polycyclic aromatic hydrocarbons, but we also find silicon monoxide SiO and silicon carbide SiC. This proves that silicon chemistry happens spontaneously in the vacuum of space. However, these are simple molecules. We do not see the precursors to amino acids or nucleotides made of silicon. The cosmic abundance of carbon-based organics suggests that the universe itself favors carbon for complex chemistry. The building blocks of carbon life are raining down on planets everywhere, carried by comets and meteorites. Silicon building blocks are not arriving in the same way. They are arriving as rocks. This gives carbon a head start on any forming world. The universal solvent, water versus others. Water is often called the universal solvent, but this moniker is another form of chauvinism. Water is actually a rather aggressive chemical. It breaks down proteins and DNA over time. Hydrolysis. Life on Earth spends a lot of energy repairing water damage. A solvent like liquid methane is much gentler. It doesn't attack chemical bonds. In a methane environment, fragile molecules that would be destroyed on Earth could survive for eons. This implies that silicon life, if it uses a gentle solvent, might not need the robust repair mechanisms that carbon life does. It could be more fragile, yet longer lived. The definition of a good solvent depends entirely on the chemistry you are trying to protect. For silicon, water is acid. Methane is a cradle. Conclusion: the open mind. In the final analysis, carbon chauvinism is a logical starting point but a dangerous conclusion. It is logical because carbon is objectively the most versatile element for chemistry as we understand it. It forms the most bonds, the most diverse structures, and works in the most abundant solvent, water. However, to conclude that it is the only way is to bet against the creativity of the universe. We have explored a tiny fraction of the cosmos. We have drilled into the crust of only one planet. We have analyzed the atmosphere of only a handful of worlds. The possibility of silicon life, whether on the frozen plains of Titan, in the high-pressure depths of a super-Earth, or in the form of a machine civilization, remains a tantalizing hypothesis. It challenges us to look beyond the mirror, to stop looking for reflections of ourselves, and to start looking for the truly other. Whether we find it or not, the search itself forces us to understand the fundamental principles of matter and energy that govern existence. It forces us to ask not just are we alone, but what does it mean to be? The universe may be filled with life that is stiff, slow, and made of sand, thinking thoughts as enduring as the mountains, waiting for us to shed our carbon bias and say hello. The nature of scientific inquiry demands that we remain agnostic until the data is in. We know carbon works. We know silicon has potential but faces hurdles. The gap between potential and reality is where the thrill of discovery lies. As our telescopes become more powerful and our probes venture further into the dark, we must keep our minds open to the possibility that the rocks we walk on might, on another world, be the ones doing the walking. The story of life in the universe is just beginning to be written, and it may have more than one author. Geological implications of silicon life. If silicon life were to exist on a planet, the geological record of that world would be fundamentally altered. On Earth, biology drives the carbon cycle. Plants pull CO2 from the air, and when they die, they can form coal or limestone. A silicon biosphere would drive a silicon cycle that is distinct from the abiotic geological cycle. We might expect to see strange formations of silica that cannot be explained by volcanic or sedimentary processes, essentially silicon coral reefs, or vast forests of crystallized structures. The differentiation between a biological silicon formation and a geological one would be subtle. Crystallization is an ordering process that mimics life. A snowflake grows, but it is not alive. A silicon organism might look remarkably like a crystal. The distinction would lie in the thermodynamics. Is the structure formed to dissipate energy and increase entropy? Or is it actively maintained against the gradient? Finding unnatural quartz formations on an exoplanet could be the smoking gun. Synthetic biology and the future. The most likely place we will see silicon life first is not in space, but in a lab. Synthetic biology is moving toward xenobiology, the creation of biological systems that do not exist in nature. Scientists are already experimenting with incorporating silicon into carbon scaffolds. If we can engineer a bacterium that uses silicon in its metabolism, we will have proven the concept. This would not only answer the astrobiological question, but could revolutionize materials science. Imagine bacteria that can excrete silicone rubber or build computer chips. The merger of silicon and carbon biochemistries could lead to a new era of biotechnology, where the distinction between the organic and the inorganic is erased. This potential future validates the study of silicon life not just as a search for aliens, but as a search for new capabilities for ourselves. The limits of imagination. Ultimately, our speculation is limited by our understanding of chemistry. There may be exotic states of matter, such as quark-gluon plasmas or neutron-degenerate matter, where complex structures can form that we cannot even conceive of as chemistry. Silicon life is the, quote, conservative alternative. It is the alternative that still plays by the rules of atoms and electrons. Beyond that lies the truly unknown. But within the realm of atomic matter, silicon stands as the lonely prince, the only element with even a fighting chance to challenge the king that is carbon. The universe is vast enough for both. To deny the possibility is to deny the vastness itself. We continue to look, and in looking, we learn more about the precious, complex, and adaptable nature of the carbon life that allows us to ask these questions in the first place. Scientific nuances of bond energies. To provide a rigorous scientific account, we must look at the bond dissociation energies. The CC bond has an energy of about 347 kilojoules per mole. The C-Sci bond is weaker, at roughly 226 kilojoules per mole. This 100 kilojoules per mole difference is significant. It means C-Sci bonds break much more easily under UV light or thermal stress. However, The SiO bond is a powerhouse at 460 kilojoules per mole, significantly stronger than the CO bond, 360 kilojoules per mole. This explains why silicon prefers to bond with oxygen rather than itself. For a silicon organism to avoid turning into a solid rock of silicon oxide, it must prevent oxygen from snapping into that bond. This requires an environment totally devoid of oxygen. This is why the reducing atmosphere is a prerequisite for silicon life. In the early history of the solar system, many planets had reducing atmospheres. It is possible that silicon life could have started, only to be wiped out when oxygen became prevalent, as happened during Earth's Great Oxidation event, which killed off many anaerobic carbon organisms. Silicon life might be the loser of cosmic evolution, a relic of the early oxygen-free universe, hiding in the dark corners where the corrosive gas of oxygen has not yet reached. The final verdict. Carbon chauvinism is a heuristic that has served us well. It focuses our resources on the most likely targets, Earth-like planets. But science is about breaking heuristics. It is about finding the exception to the rule. Silicon life represents the ultimate exception. It is the test of whether biology is a specific phenomenon of carbon or a general phenomenon of complexity. Until we turn over the rocks on Titan or drill into the crust of a super-Earth, silicon life remains a ghost, a theoretical possibility haunting the periodic table. It reminds us that what we consider normal is simply what we are used to. In the grand periodic table of the cosmos, carbon is our home, but silicon is the horizon. And the horizon is always worth exploring. The sheer density of information required to fully flesh out the concept of silicon life extends into every branch of science. From quantum mechanics governing the electron shells to the astrophysics of planetary formation, every discipline has a say in this debate. We find that the universe is biased towards carbon, but it is not exclusive. The laws of physics allow for the existence of silicon complexity, provided the conditions are right. Those conditions are rare, extreme, and hostile to us, but they exist. Therefore, the probability of silicon life is non-zero. And in an infinite universe, non-zero is enough. We are the carbon observers, waiting for the silicon sign. The dialogue between these two elements, carbon and silicon, defines the technological history of humanity, from stone tools, silicon, to computer chips, silicon, used by biological hands, carbon. Perhaps the final step in this relationship is meeting a being where the silicon is not the tool, but the master. Evolutionary pressures on silicon. If silicon life did arise, how would it evolve? Evolution requires mutation and natural selection. Mutation comes from errors in information copying. If silicon genetic molecules are more stable due to cold temperatures, or less stable due to weak bonds, the rate of evolution would differ. A silicon species might remain unchanged for eons, or it might radiate rapidly in a chaotic environment. The pressures would be different. On Earth, organisms compete for sunlight and food. On a dark, silicon-friendly world, organisms might compete for heat or rare trace elements. The survival of the fittest would apply, but the definition of fit would be unrecognizable. It might mean most resistant to crystallization, or most efficient at harvesting thermal gradients. The evolutionary tree of silicon would look less like a branching oak and more like a creeping lichen, slow, durable, and clinging to existence in the face of entropy. Concluding thoughts on the universal tapestry. The tapestry of the universe is woven from the elements forged in the hearts of dying stars. Carbon and silicon were born in the same stellar furnaces, blasted out into the void, and coalesced into planets. On one blue planet, carbon woke up and started wondering about its origins. It is a poetic symmetry that the element carbon asks questions about the element silicon. Whether silicon ever asks back is a mystery for the ages. But the very act of asking expands our understanding of the cosmos. It forces us to appreciate the delicate constraints that allow us to exist. It highlights the miracle of the CC bond, the magic of water, and the frighteningly narrow window of conditions that we call habitable. Carbon chauvinism, in the end, is just a recognition of our own fragility. We cling to carbon because it is all we have. But the universe is not so limited. It plays with a full deck of elements, and somewhere, in the cold dark, it may have played a different hand. The study of silicon life is the study of the road not taken, and science demands that we travel down every road, no matter how rocky or strange it may be.